China just assembled a fully livable 10-story apartment building, walls, windows, balconies, plumbing, electrical wiring in 28 hours and 45 minutes. In London or New York, that same building takes 3 years from permit to keys. You heard that right. But the speed is not the story. The story is the man who built it, the earthquake that remade him, and the question he asked that the global construction industry had spent 100 years avoiding. That question starts in the rubble of Sichuan. The man the earthquake made. Here is what you need to know about Zhang Yue before we talk about a single building. He was not a construction man. He ran an air conditioning company. Broad Group, based in Changsha, was one of China's leading HVAC manufacturers, climate systems, industrial cooling, engineering precision applied to temperature. That was his world. Not walls. Not the question of whether the thing people sleep inside will still be standing when the ground starts moving. Then the ground started moving. May 12, 2008, Sichuan, China, magnitude 7.9, and when the shaking stopped, 70,000 people were dead. That is roughly the entire population of Cambridge, England, wiped out in under 2 minutes, most of them buried under concrete, under the buildings that were supposed to protect them. Zhang Yue watched the footage. He watched rescue teams pulling children out of school buildings that had pancaked flat floor, pressing down on floor like a stack of collapsed shelves. He watched apartment blocks fold in 40 seconds. He watched engineers explain, calmly, that the buildings had met code, that this was just what concrete does when the earth moves hard enough. And that is where something broke in Zhang Yue. Not grief, though there was grief. Something more dangerous than grief. A question. Why are we still building this way? Here is the part that most people never stop to think about. The technology to build differently already existed in 2008. Steel modular construction had been demonstrated. Prefabricated systems had been tested. The engineering knowledge was there. But the construction industry, not just in China, but everywhere on Earth, had spent a century perfecting concrete, scaling concrete, writing its codes around concrete, and training its workforce on concrete. Changing that system felt like turning a cargo ship with a rowing oar, so nobody seriously tried. Zhang Yue was not interested in the cargo ship. He pulled his engineering teams away from air conditioning. He redirected Broad Group's manufacturing infrastructure. He set a single target build a system so obviously superior that no engineer standing in front of a camera could ever again explain a collapse by saying the building met code. Years of failed prototypes and scrap designs followed. There were moments the project looked like a billionaire's vanity, ambitious, expensive, and quietly going nowhere. Then it started working. And what he built didn't just answer his question. It made every conventional construction method on Earth look like it belongs in a different century. But before you see what Broad Group built, you need to understand what they built it out of, because the material is the part that silences every skeptic in the room. The factory that swallowed the construction site. Picture a shipping container. You have seen them on trucks, on cargo ships, stacked in ports. You know the size intuitively. Now imagine that container is not carrying goods. It is the building. A fully finished slice of a floor, walls in place, conduit already run, windows fitted, balcony railing welded on. You crane it off a truck, bolt it to the one below, and you are not assembling a building. You are stacking a building, like flat pack furniture, at skyscraper scale. That is Broad Group's system, and it starts not on a construction site, but inside a factory. The Broad Group manufacturing facility in Changsha covers 230,000 square meters. That is roughly 32 football pitches under one roof. Inside that building, every component of every Broad Group structure is built in a controlled environment. No rain delays, no site accidents, no delivery stuck 3 cities away. When a module leaves that factory, it is not a raw component waiting to be finished on site. It is a finished room waiting to be stacked. Here is the detail that puts everything into perspective. Traditional construction works outside in. You pour a foundation, raise a frame, run conduit through walls after the fact, hang drywall over wiring, someone else will inspect next month. Every trade works in sequence. Every delay compounds. Every mistake gets buried in a wall where nobody will find it until something stops working. Broad Group works inside out. Every system is installed, tested, and verified before the module ever leaves the factory. The building is essentially complete before it touches the site. Now here is where the skeptic in the room usually speaks up. And the skeptic has a reasonable point. Modular construction is not new. The British tried it after World War II to solve a housing crisis. The Soviets built entire cities out of prefabricated concrete panels called Khrushchevkas. The results were not inspiring and widely abandoned within a generation. That skeptic is right to raise it, because here is what makes Broad Group different from every prefabricated attempt that came before it. The material. Broad Group does not build in concrete. They build in steel. High-grade, precision-engineered, factory-welded steel frames. And the difference in structural performance is not incremental. Steel modules built to Broad Group specification carry loads 100 times greater than an equivalent concrete structure under stress. 100 times. If a concrete building and a Broad Group steel building stood side by side, and you applied the same catastrophic force to both, the concrete building reaches its failure point before the steel building has even begun to strain. Then there is the earthquake data. Independent seismic engineers, not Broad Group's own team, external verifiers, tested the system against simulated seismic loads. The result was verified resistance to a magnitude 9 earthquake. The Sichuan quake that killed 70,000 people was magnitude 7.9. A magnitude 9 releases roughly 16 times more energy. The buildings Zhang Yue now builds would have stood in Sichuan. Not probably, not likely. They would have stood. And then there is the number that stops every conversation cold. Structural lifespan. A well-built concrete structure lasts between 50 and 100 years before integrity becomes a genuine engineering concern. Broad Group's steel modular system is rated for 1,000 years. 1,000. Say that number back to yourself. That is not a marketing figure. That is the corrosion rate of the treated steel, the load-bearing degradation curve, and the joint integrity timeline calculated by structural engineers and expressed as a lifespan. A building assembled in 28 hours is engineered to outlast every concrete skyscraper currently standing on Earth. And Broad Group's factory model cuts construction waste by 90%, 90% less rubble, 90% less landfill from a single build. Here is what most people get wrong about this technology. They hear prefabricated and picture the gray Soviet housing blocks. Compromise. Buildings that work on paper but feel like prisons to live in. What they do not picture is a 10-story finished apartment block rising from an empty site in 28 hours and 45 minutes while the neighbors are still watching from across the street. But Broad Group is only half of what China has built. Because running in parallel, in a factory on the other side of the country, a completely different technology is solving the same problem in a completely different way, and together they represent something the construction industry has never had to face before. Two simultaneous answers to the question it spent a century refusing to ask. The printer that builds houses while you sleep. Forget everything you picture when you hear the words 3D printing. Forget the desktop machine making plastic figurines. What Winsun built in Shanghai is not a printer in any sense your instincts are prepared for. It is a gantry system. Think of the arm that moves across a CNC machine, but scaled until it spans an entire building footprint rolling on rails, dragging a nozzle the width of your forearm, laying a continuous ribbon of material in precise, programmed layers back and forth, course by course, until a wall is standing where nothing stood an hour ago. And unlike a human crew, it does not stop for lunch. The material coming out of that nozzle is not virgin concrete. It is a blend of recycled demolition waste, crushed brick, salvaged aggregate, industrial byproducts that would otherwise go to landfill, combined with a fast-setting cement, engineered specifically for extrusion. Too wet, and the layers slump, too dry, and the nozzle clogs. Winsun spent years finding that ratio. The result sets in minutes. bonds layer to layer under its own chemistry, and meets Chinese residential building code. Here is what makes this genuinely extraordinary. In 2014, Winsun printed 10 complete livable houses in a single 24-hour run. Not prototypes, not shells. Livable houses, walls, internal divisions, door and window openings printed, completed, and structurally certified in one continuous operation. A traditional crew building 10 houses simultaneously would need months, dozens of workers, and a logistics operation across 10 separate sites. Winsun needed one machine and one day. The material savings are just as significant. Conventional construction wastes between 15 and 30% of everything purchased. Winsun's nozzle deposits exactly what the design calls for, nothing more. The result is a reduction in material use of between 30 and 60%. To put that in human terms, the material saved on 1,000 printed houses is enough to build 300 to 600 additional ones. From the same budget? Then came the problem that every engineer in the room already knew was coming. Printed concrete walls carry vertical loads exceptionally well, but concrete is weak under tension, the flexing forces from wind, thermal movement, and seismic activity. Traditional construction solves this with embedded steel rebar. Threading rebar through a printed wall is possible, but complicated, and it remains one of the genuine unresolved challenges of the technology. It is not a deal breaker. It is an 18 to 36-month development problem with multiple solutions currently being tested. But here is what makes that limitation significant in a way most people miss. The countries that need this technology most, the ones with the largest housing deficits, the most constrained labor markets, the least time to wait, are also the ones most exposed to seismic and extreme weather risk. Solving the tension problem is not a nice-to-have. For Winsun, it is the difference between a remarkable machine and a truly universal one. And that is exactly the kind of pressure that produces breakthroughs fast. Because Winsun is not working in isolation, Broad Group is solving the same problem from the opposite direction. Together, these two systems represent something the global construction industry has never been forced to confront: two simultaneous, proven, scalable answers to the question it spent a century refusing to ask. But to understand why those answers matter, you first need to understand the true scale of what they are answering, because the housing crisis is not a policy talking point. It is a number so large it barely fits inside a single sentence. 100 million doors that don't exist. 100 million. That is the current global shortfall in housing units. 100 million homes that need to exist and do not. To hold that number, picture the entire population of Germany, France, and the United Kingdom combined, with nowhere to live. That is not a projection. That is the number housing economists are working with right now, today. And it is getting worse. Urbanization is accelerating across Southeast Asia, Sub-Saharan Africa, and South Asia faster than conventional construction can respond. The UN estimates 2.5 billion additional people will be living in cities by 2050. 2.5 billion, roughly the combined populations of China and the United States, all moving into urban areas that do not yet have the housing stock to receive them. And the industry tasked with building it is slower, more expensive, and more labor-starved than at any point in the last half-century. Here's the part nobody talks about. Construction is one of the least automated industries on Earth. Walk onto a conventional site in London or Sydney, and you are watching methods a builder from 1975 would recognize. The process: pour, wait, build, wait, fit, wait, inspect, wait, has not structurally changed in 50 years. And the workforce that performs it is aging out faster than it is being replaced. And here is where it gets genuinely alarming. In China, the generation that built the country's extraordinary infrastructure over the last 3 decades is retiring. The generation behind them is not going to construction sites. And China has 260 million people living in urban areas, built from concrete rated to last 50 to 100 years. The replacement clock is already running. This is not a future problem. It is a present one. Now here is where the market numbers make the stakes real. The global modular construction market hit $95 billion in 2025. By 2034, it is projected to reach $175 billion. Strip the finance language away, millions of families in countries that cannot afford to wait 3 years for a mid-rise are watching what China built and making a decision. That growth is not coming from Europe or North America. It is being driven by China, the Gulf states, and Southeast Asian governments that have concluded conventional construction is simply not a viable path forward. The cost curves tell the rest of the story. Traditional construction gets more expensive every year as labor costs rise and regulation compounds. Factory-built and printed construction gets cheaper as systems scale and material science matures. These two curves are moving toward each other. In some markets, they have already crossed. China crossed that line first, and the result is a construction ecosystem now operating in a different economic reality to the rest of the world. Which brings you back to the number that started this video, 28 hours and 45 minutes. Now it is time to walk through exactly what happened. Because when you see the mechanics of how a 10-story finished building goes up in less time than it takes to fly from London to New York, it stops feeling like a trick and starts feeling like the most obvious thing in the world. The 28-hour stack. Picture an empty site, cleared ground, a prepared foundation, and a fleet of flatbed trucks lined up down the road. Each truck is carrying a module, not a load of bricks, not a pallet of raw materials, a finished room, walls already up, wiring already run, windows already seated in their frames, balcony railing already welded. The room is complete, it just isn't stacked yet. This is where the broad group system does something that stops engineers mid-sentence when they see it for the first time. The modules arrive sequenced, not by floor number, by crane window. Every lift is scheduled to the minute. The crane operator is not waiting for the next module to show up. The next module is already rolling through the site gate before the previous one is fully bolted down. The choreography is tighter than most people imagine construction can be. Here is the detail that puts the speed into perspective. On a conventional high-rise, the structural frame alone before a single wall is built, before a single pipe is run, takes months. Concrete is poured floor by floor, and each pour has to cure before the next floor begins. Cure time for structural concrete is typically 28 days per pour. 28 days per floor. On a 10-story building, that sequencing alone represents the better part of a year before the finishing trades even arrive. Broad Group eliminates that entirely. There is no cure time. There is no sequencing delay between structure and fit-out, because the fit-out is already done when the module leaves the factory. The crane lifts a finished floor into position. The connection team bolts it to the floor below precision-engineered joints designed to align on the first drop. Then the crane is already lifting the next one. 28 hours and 45 minutes later, a 10-story finished apartment building is standing where there was empty ground the morning before. Now here is what most people get wrong when they hear that number. They assume shortcuts were made. They assume it is fast because something was sacrificed. But the earthquake resistance data, the structural lifespan projections, the waste reduction figures, none of those are the numbers of a system that cut corners. They are the numbers of a system that moved the work somewhere the construction industry never thought to look. Off the site, into the factory, out of the weather, out of the chaos, into a controlled environment where precision is the default. But as extraordinary as the build time is, it is still not the biggest obstacle this technology faces. The biggest obstacle has nothing to do with engineering, and it is the reason a method capable of housing millions of people faster, cheaper, and safer than anything else on Earth is not yet the global standard. Because the wall in its way was not built with steel or concrete. The wall that wasn't built it was written. Here is what makes this incredibly frustrating and clarifying at the same time. The technology works. The earthquake data is verified. The build times are documented. The cost curves are moving in the right direction. There is no credible engineering argument against modular and printed construction at scale. The case is essentially closed. And yet, in London, a mid-rise apartment building still takes 3 years from permit to keys. In New York, the same. In Sydney, in Toronto, in Paris, the same crews, the same sequences, the same process a builder from 1975 would walk onto and immediately recognize. So what is actually in the way? 3 things, and none of them are technical. First, building codes. The regulatory frameworks that govern construction in most Western countries were written for conventional concrete and timber methods. They specify not just what a building must achieve load-bearing capacity, fire resistance, thermal performance, but how it must be built. Modular steel systems and printed concrete walls frequently meet the performance requirements while failing the method requirements. The code does not ask whether the wall holds. It asks whether the wall was built the way the code imagined. Rewriting those codes requires political will and years of regulatory process. Nobody inside the current system has sufficient incentive to move quickly. Second, supply chains. Every major developer, every large construction firm, every materials supplier operates inside an ecosystem built around conventional construction. Concrete suppliers, timber merchants, bricklaying subcontractors, scaffolding companies, an entire economic infrastructure exists to service the old method. Switching to factory-built modular construction does not just change how buildings go up, it makes large parts of that infrastructure redundant. The people inside it know this, and they have lobbyists. Third, and here is the part nobody wants to say plainly, the slowness is profitable. A 3-year build timeline is not just an inefficiency, it is a revenue model. Consultants, project managers, specialist subcontractors, financing arrangements, charging interest across multi-year build periods. The duration of conventional construction is not an accident. It is a feature for everyone being paid by the month. The countries watching China most carefully are not the ones you would expect. Not Germany, not the United States. They are the Gulf states, Vietnam, Indonesia, Nigeria, Ethiopia, countries with housing deficits so acute and labor markets so constrained that they cannot afford the luxury of institutional inertia. They are not debating whether to adopt this technology. They are debating how fast. And that calculation changes everything about where this story ends. The city that builds itself. Zoom all the way out. 100 million missing housing units. A construction workforce aging out of the industry. A climate demanding less waste, less material, less of everything the old method generates by default. And 2 technologies, one stacking finished rooms at skyscraper scale, one printing walls from recycled rubble while the city sleeps, that together answer every part of that problem simultaneously. This is not a technology story. Not really. Here is the question that actually matters. If the engineering works, and it does, and the economics are moving in the right direction, and they are, then what kind of world becomes possible when the friction is finally removed? Picture a government in Southeast Asia with 3 million people in inadequate housing. Right now, under the old model, that problem has no realistic solution. The labor is not there. The time is not there. The money, at conventional construction costs, is not there. Under the broad group and Winsun model, that problem has a factory answer. The constraint shifts from the chaotic, weather-dependent, labor-hungry build site to a factory floor where throughput is a function of investment and process, not of how many bricklayers you can find. Here is the closing argument that Zhang Yue has been making since he stood in the rubble of Sichuan. We do not have a housing problem because we lack the ability to build. We have a housing problem because we locked ourselves into a method that is slow by design, wasteful by habit, and protected by a system that profits from its own inefficiency. The proof that a better way works is not a blueprint. It is not a proposal. It is a standing building. You can walk into it. You can live in it. China built a 26-story tower in 5 days. London takes 3 years for a mid-rise. That is not an engineering gap. That is a choices gap. The rest of the world is still pouring concrete and waiting for it to cure. 28 days per floor. While China stacks 10 in a day,